Okay, this video is about coordinate systems. There's a bit of kind of theory, general stuff about the topic and type of problem, and then I'm illustrating with a work solution. You'll also find on the channel on my channel other videos with work solutions. But this one is about parabolas. And now these questions are quite hard, really. Um, they're really sort of an extension of the coordinate geometry type of problem that we get in A level. Um, but those tend to deal with well curves and straight lines. That's the same way, but the curves tend to be maybe quadratics, cubics, or circles. Um, and here we're looking at parametric equations defining curves. That's one of the differences. But the other thing that kind of makes these things harder is that we've got sort of lots of kind of parameters and variables and unknowns, and kind of understanding how all these things work together is quite difficult. So hopefully this is something that I can try and unpick for you. And if you get a view of how that works, then hopefully that will make these problems a little bit more a bit easier to understand and to solve. And now the conic sections, or the type of curves that we get with these kind of problems, are parabolas, hyperbolas, and ellipses. I suggest that in the first place, as you practice these things, you're probably better to stick to one kind of curve. I suggest parabolas. And then once you've kind of developed your understanding and your knowledge and your method, then it would be relatively straightforward to actually extend that to hyperbolas and ellipses. So this one is just about parabolas. So let's have a look. So here we've got a parabola in the red. Okay, now these things are we're often given that these are given the Cartesian equation for these in the form of y squared equals 4ax. And but this comes from a parametric equation. I mean, all these kind of curves where we've got two values of y for a value of x, they tend to come from parametric equations. And so so if you're told that y square that the curve, for instance, is y squared equals 12x, then that tells you that this value of a is 3, and therefore the parametric equations are x equals 3t squared and y equals 2 times 3, 6t. Okay, so that's that. Now, what is a parabola? Basically, it's the locus of points where every point on the parabola is the same distance from a fixed point S. I've called it F here, actually, and this fixed straight line called the directrix, which is this line coming down here. So this point here would be equidistant from there and there, and pick any other point on the line, and the same thing would apply. Now, these problems tend to be all about, well, not so much the curves. The curves give rise to information that we then use, but it kind of hangs on the straight lines that are related to these, and that the straight lines that we tend to be interested in are, well, given 2 points on the line, which is a typical type of problem, is we've got the tangents. Those are the ones there in black. We've got the adjoining line between P and Q, 2 points on the parabola. We've also got the normals at those points as well. And going along with those lines, We've got any number of sort of intersections going on. You know, here the two normals intersect. The normals intersecting the the axis, the x-axis in that case. There'll be intersecting the y-axis down there as well. You know, and it goes on the tangent there, intersecting the y-axis, um, and here intersecting the directrix. And well, so you can see for yourself, you've got a variety of different points. Here we got the point where the two tangents meet. So these problems tend to be all about the straight lines associated with the curve and where they meet, and then what that gives rise to. So, so if we have a look at some things we can glean from all this, right? Okay, the gradient of the tangent um, is 1 over t. So we can derive that by finding dy dx, which we find from parametric version of the equations, which is dy dt times dt dx. So we can derive that. And I think it's fair to say actually with these problems is that for the curve you're more interested in this in the parametric form of it than you are of this. The Cartesian tends to be given to you really so so that you can we've got a way of finding a. It's just but it's kind of normally the parametric version that you're concerned with for the curve. However, all the other lines, then obviously they're straight lines. Um, so that's the tangent. The normal is going to be therefore gradient minus t, and the general form of the tangent. Um, well, y minus y1 being that, is the actual point at uh, t for parameter t equals 1 over t into x minus x1. And if we actually work that through, that's going to give us this ty equals x plus at squared, which is the general form of the equation of the tangent, okay, at t. Right, so that is useful. And this equation, well, you can derive it. Yeah, it's actually quite useful to memorize this, I think, because it save you a bit of time. Um, so yeah, good thing to memorize. I'm not a great one for memorizing stuff that you can easily derive, but for this one, I think it's a good idea. Okay, so generally speaking, what we are given for points P and Q is we are given their coordinates, which kind of links in with this, doesn't it? But we're given coordinates, but they will be given in not as points, generally speaking, but in this sort of form here. All right. Now, very often that can give us that can link us back to the parameter t. So we're going to work out the value of t for these particular points. So if we are told that, um, we may not be told A, yeah, but anyway, if we work these points through, that's going to give us that p squared is equal to at squared. Yeah, just that's the correspondence. And 4p is equal to 2at the same way. And therefore p equals at over 2. 80 squared over 4 equals 80 squared, therefore A equals 4. Yep, so we've derived that from these two equations, and then P squared is equal to 4T squared. T equals P over 2 at the point P. All right, and T equals Q over 2 at the point Q. Now we don't know P and Q, but we don't know little p and little q. But there's lots of stuff that we can do just by knowing this. Um, Now, one thing we can do is we can derive well, what I call the particular equations. This is kind of more to do with differential equations, really, but a particular equation, we talk about general solutions or general equations, which have, as well as our two variables, will have a number of unknowns in, um, which we for which we need to resolve in order to get ourselves a useful equation. Um, So, and we do that by sort of realizing our boundary conditions, and that's kind of what we're doing here. So I put this in apostrophes here, particular equations, because when we realize this, the tangent equation for, let's say, t equals p over 2, we get this. Now, this is all right. We don't know p, but P is a real point. We know the coordinates of P. We know the coordinates of P are given to us here. It's just that we don't know the value of P. All right. So it's you have to kind of get this in your mind that actually we are given, this is real information that we're given, is that the coordinates are defined in terms of P. So it's not a parameter. It's not a variable. It's an unknown. Yeah. It's something definite, but we just don't know what it is. All right. So if you can sort of kind of understand that concept, then that I think helps. So yeah, so that will give us that, and we can rearrange this, obviously, and make it explicit in y or whatever we want. The normal at p, in the same way, if we substitute um, minus t in there, y minus y1 equals um, the gradient times into x minus x1. That's what we've got there. And again, we can rearrange that. So I've got two real equations for those straight lines that sort of emanate from the point P. We've also got this line PQ, which has got a gradient of that. That's just the rise over the run between those 2 points P and Q. Um, and again, y minus y1, so that's the the y coordinate times the gradient equals the gradient times x minus x1, which is that there. Okay, so that's kind of the generality of it all. And so, yep, we're finding out these uh, equations, but we're finding them out in relation to usually not actual constants and numbers, but in terms of these P and Q, which are real numbers, but we don't know what they are. Right, okay, so just to recap on that, Cartesian equation of the parabola, we know in parametric form as being that Cartesian equations of lines are in terms of, in this case, P and Q. Right, so that's the general stuff. So let's go on and have a look at a worked example. Right, so the parabola C has equation y squared equals 16x. Distinct points that, and that's always p squared and 4p, by the way. Q squared and 4q lie on C, non-zero. The tangent to C at P and the tangent to C at Q meet at this point here. Show that the area of the triangle, PQR, is 1331. So this is a sketch of what we have. And so these are the tangents, and they meet at this point here, minus 28, 6. All right, so let's just remind ourselves a general point is that. Well, it's the Cartesian version, isn't it? The um, parametric form, it's that. The Cartesian equation of this curve is that A is a positive constant, and the parabola is the set of points. Um, where, as I said before, a point on the curve is the same distance from the focus as the directrix, and the vertex is also at 0, 0. And all these problems, incidentally, we tend to deal with curves that are sort of lying on their side, if you like this. I mean, all this argument, can be extended to curves like this, which are going to be one of the form y equals x squared. Um, but the problems like that are pretty rare, so we'll just stick with this. Right, so okay, so what we've got here, therefore, is that y squared equals 16x. So that's of the form 4ax, so we know that a equals 4 on this. So our parametric version of the line, these are our coordinates in relation to t, are going to be that 4t squared and 4t. So when we compare this, this to this, we can see from that that t is going to be p over 2, and t, and at q, that's at p, and then at q, t is q divided by 2. Right. Okay, so so we have evaluated. We've evaluated the points P. We worked out what they are, but in terms of P and Q. So the general equation of the tangent is this, as we said before. That's the thing that we can derive, but also remember. And therefore, at P, when T is equal to P over 2, then if we just substitute that into here, substitute 2 into here, we're going to get that, and then that's going to give this, which is what I'm calling the particular equation of the tangent. All right. Right. Okay. So now, so this tangent goes through the point 28, 28, 6. Just move that down a bit. So we can sort of realize this point in the equation. When we do that, we're substituting these points in for y and for x. Work that through, rearrange it, and it gives us this quadratic. Now, this is rather reminiscent of things that we've done at A level, where we're often looking at the intersection of a line and a curve, and either the line or the curve will have some unknown value in, which is generally denoted as by the letter K. And if, for instance, we are told that the line and the curve meet or they touch, so the line is a tangent to the curve, then what we know there, that gives us the knowledge that when we look at the equation of intersection, the discriminant will be 0, because a discriminant of 0 will just give us one solution. Right, so this is very similar in that sense to this. So this is that equation, but in terms of P. Now, so we can factorize that, and we solve for P minus 4 or 7. Now we've got exactly the same equation for Q. So Q is going to be either minus 4 or 7. So therefore, we can conclude from that that 1 is going to be, P is going to be 7, and Q is going to be equal to minus 4, or maybe the other way around. Well, since P is, so the big P, the point P is in the first quadrant, it seems sensible to take P as 7 and Q as minus 4. I think if you'd got them the other way around, I think it wouldn't affect your answer. But so that's what we're doing. It just seems more logical. Right. So just to look at this another way, incidentally, is given this particular curve that we've got here and this point here, there are only two tangents that we can draw from this point. This is one. Yeah. This is the other one. The top one will meet the curve at this point, and the other one will meet the curve at that point. So that's kind of looking at the problem the other way round. All right. Anyway, we've done that. We've got our value of P and our value of Q. And if we use those values back in the equation of the line, we can therefore work out that P is going to be that point, 49.28. Q is that, and that's R is what we're given. All right, so we've got the 3 points of this triangle that PQR. Now, at this point, it's actually quite useful to be able to use the coordinates form of the area of the triangle, and which is here. We may be familiar with it. If not, it's worth remembering this as well. It's kind of not too bad. We got half into x into the difference of the y's plus x into the difference of the y's and x into the difference of y's 3 times, but we got one, we got one, two, three, two, three, one, three, three, oops, three, one, two, sort of cycles round. So that might help you to remember that. And so when we plug in the values from these points here into that, then sure enough, we get 1,331 as the area of that triangle. Okay, so that basically is it. Um, so yeah, so the thing is we're kind of going to be working with these P's and Q's or whatever the values are in your particular problem. Um, but very often, we'll either be expressing an answer in relation to P. Sometimes we have to do it in relation to A as well if we don't know what A is. Um, but uh, they're real values, and so you kind of just work through them on the basis that these are actual values, and then that should work you through to your solution. Okay, so I hope that has been useful. Look out for more examples, and thanks for watching.